Hello everyone, welcome to another video session class. So in today's class we will study about Clemmensen reduction and Wolff Kishner reduction. So both these reactions are reduction reaction, that is addition of hydrogen, okay, or gain of electron, you can say, in classical modern concept or electrical concept. So that means some changes will be there after completion of the reaction. Okay, so Clemmensen reduction, we know Clemmensen reduction, the reagent used are zinc amalgam and HCl. Okay, so let us just start. We will see in the upcoming slides what is Clemmensen reduction and what is Wolff Kishner reduction. Okay, so let us start. So you see here zinc amalgam, then HCl. Okay, so Clemmensen reduction is a chemical reaction described as a reduction of ketones or aldehyde to alkanes, okay, using zinc amalgam and hydrochloric acid or HCl. Okay, so zinc amalgam means zinc with mercury. Amalgam means mercury with some metal. Okay, amalgam means mercury with some metal. So here metal is zinc, so it is zinc amalgam. Okay, some metals if attached to the mercury, that is known as amalgam. Okay, so we are going to use this zinc amalgam and hydrochloric acid as a reagent. Okay, so Clemmensen reduction, so here what is happening, either aldehyde or ketone is going to convert to the simple alkane. Okay, here you see ultimately goal of the Clemmensen reduction is to convert the carbonyl group to the methylene group. This is methylene, CH2 group. Okay, so Clemmensen reduction is an organic reduction reaction shown by both aldehyde and ketones, but carboxylic acid group can't be reduced by this method. Okay, so you have to remember that is carboxylic acid can't be reduced with this zinc amalgam, that is through this Clemmensen reduction, but the COH group can be reduced by treating with soda lime, NaOH plus CaO and then heating. Okay, that can be done. Reduction of this COH group can be done by using this another contest. Okay, here what is happening, C double bond O group of aldehyde and ketone is reduced to CH2, that is known as methylene group, by Clemmensen reduction. Zinc amalgam and concentrated HCl, that is zinc Hg and concentrated HCl is used as the reagent for the Clemmensen reaction. Alkenes and alkynes don't react with Clemmensen reagent. So this is one note, alkenes and alkynes never react with Clemmensen reagent. So here you see that these two reactions are the Clemmensen reduction reaction. C double bond O, that is carbonyl group, that is converted to CH2, okay, CH2 group by the help of zinc amalgam and HCl. Here also see acetophenone is converted to ethyl benzene. So here see C double bond O group, this carbonyl group is converted to CH2 group, CHH. Okay, so that is the Clemmensen reduction. So let us see the mechanism. So the concentrated acid is required for the initial protonation. Amalgamation of zinc prevent the protonation of hydrogen. Halo acids, that means HCl, are more effective because they form complex with zinc metal and also provide medium for second zinc metal. So here two zinc metal will attack. Ultimately there will be a zinc bed which will attack this carbon, okay, carbonyl carbon. So here you see carbonate mechanism, this one is carbonate mechanism, is a radical process and reduces the happenings on zinc metal surface. The reduction takes place at the surface of the zinc catalyst. So this is zinc catalyst, okay, zinc surface, this is zinc surface. So here what will happen, first this zinc will attack this carbonyl carbon, that means ultimately it will attack this oxygen. Okay, oxygen, so it will attach to the oxygen. Then next ZNO, zinc oxide, will be come out and another zinc. So here it is written second zinc. Okay, one ZNO will come out and to this carbon another zinc bed or zinc will attach. Okay, C double bond Zn. Okay, then next again protonation will take place, that means this double bond will break down and this proton will attack this carbon to form CH bond. Okay, so here you see CH bond. In the next step again one more proton will attack this bond, okay, and this proton H plus will attach to this carbon. So you see this carbon is having two hydrogen, and this zinc bed zinc will come out. Okay, zinc will come out, and ultimately we will get RCH2R. Earlier the compound was RC double bond O R, okay, or R dash. So this is the simple mechanism of this reduction reaction. Okay, so next application, Clemmensen reduction of ethanol, first application. So this is aldehyde, you use zinc amalgam and concentrated HCl, it will be converted to ethane, correct, because C double bond will be converted to CH2. Here CH3 was there before, then again CH2, okay, CH2 and this H, that means another CH3. The next, Clemmensen reduction of propanol. So again another aldehyde, propanol. So here it will convert to CH3, CH2, again CH3. So it will convert to propane. Next application, benzaldehyde and Clemmensen reduction. So methyl benzene toluene is given when benzaldehyde is reacted with zinc amalgam and concentrated HCl. Okay, so methyl benzene will form from the benzaldehyde. So this is aldehyde, C double bond OH. So with zinc amalgam and HCl, it will form CH3, from CHO to CH3. So from benzaldehyde to methyl benzene or toluene. Next, Clemmensen reduction of propanone. So this is acetone, So propanone gives propane. So ultimately CH3, here C double bond O group will convert it to CH2. So this CH2, then CH3. So these are some application of Clemmensen reduction. Okay. So next, let us start Wolff Kishner reduction. So this reduction is, first what will happen, aldehyde or ketone will react with hydrogen to convert that aldehyde or ketone to hydrazone. So this is the structure, hydrazone, in presence of KOH and heat. Okay, here you remember this reaction require high temperature, around 180 degrees Celsius. So it will convert to first hydrazone, then what will happen, then it will convert to simple alkane. So here Wolff Kishner reduction in presence of hydrazone and KOH, potassium hydroxide, in presence of high temperature, it will convert to your aldehyde or ketone will convert to simple alkane. So reduction of aldehyde or ketone to alkane, here this is Wolff Kishner reaction. Condensation of the carbonyl compound with hydrazine forms the hydrazone. So condensation of the carbonyl compound with hydrazine, so this carbonyl compound will condense with hydrazine to form hydrazone, and treatment with base, so this with base, that is KOH, induces the reduction of carbon coupled with oxidation of the hydrogen to gaseous nitrogen to yield the corresponding alkane. So you will get, so ultimately after this reaction N2 will liberate. Okay, N2 will liberate, that is nitrogen gas, gaseous nitrogen will liberate. The Wolff Kishner reduction is used to convert ketones to methylene group. So here also the same, this ketone or carbonyl group will convert to methylene groups and aldehyde. That's here ketones to methylene group and aldehyde to methyl group. You remember, whenever there is aldehyde, it will convert to methyl group, and whenever there is ketone as a starting material, it will convert to methylene group. That means CH2 group. It cannot be used to reduce the carbonyl groups of amide and esters. So in amide and esters, we know there is CONH2 and COOR, that is ester. Those carbonyl groups, C double bond O group, cannot be reduced by this Wolff Kishner reduction. Next, limitation. So limitation, there are two I have given. The reduction require a high temperature. So I already mentioned it requires at least 180 degree Celsius temperature for reduction. It cannot be used for stereochemically hindered ketones. So for stereochemically hindered ketones, this Wolff Kishner reduction is will not work. Okay, cannot be used. So next, mechanism of this Wolff Kishner reduction. So first step, there is series of, you remember, in mechanism there is series of protonation and deprotonation will take place, and ultimately we will get the product as a alkane. Okay, so first step, deprotonation of nitrogen. You see, deprotonation of nitrogen. So this is the second step product, that is hydrazone. OH from KOH, that is from base OH, this deprotonation will take place. That means this H will come out with OH, okay, as a H2O, and this bond will shift to this nitrogen bond. So here you see N, then again this, as a result this bond C and double bond will break and it will acquire a carbon will acquire a negative charge. Okay, so next step what will happen, this carbon will be protonated. In the second step, protonation of the carbon, so again water molecule will come and it will give its proton to carbon, so ultimately CH bond will be formed. Okay, and here it is the same N double bond NH. In the third step what will happen, deprotonation of nitrogen. So here what will happen, again the NH, you see this in this step NH is there, so this H will come out. In the third step, again OH will attack this H, this H will come out as a proton and this will share the electron to this nitrogen double bond. So as a result N triple bond N, that is N2 will come out. Okay, water, see H, OH, water will come out, and again this bond will break down. After breaking this bond, N2 will come out and this carbon will acquire the negative charge, so C negative. Okay, that is carb anion will be formed. Then again in the last step, another molecule, another proton will attack this carbon ion to generate alkane. So here you see from this water molecule H will come. Okay, that means this electron will attack this H and ultimately it will take up this H and OH will come out as a reagent. Okay, OH, we have initial step we have given OH and at the end of the reaction we are getting OH back. Okay, OH negative back. So this is overall the reaction and ultimately we are getting product as a alkane. This alkane is the product. Next application, so synthesis of 4-N-hexyl resorcinol, which is the antiseptic, it will be SEP-TIC. Okay, antiseptic. So here you see resorcinol, from resorcinol you react that one with hexanoyl chloride, so it will form this compound. Okay, after that one you apply Wolff Kishner reducing agent, that means NH2 hydrazine along with KOH. Okay, that means your base, so that will convert that one. See here CO is converted to CH2. We know ketone will convert it to methylene group, correct? So it is 4-N-hexanyl resorcinol. Then reduction of steroid compounds. So see, this is the steroid nucleate cyclopentanoate perhydrophenanthrin. So you just do reduction here. Okay, you do reduction here, Wolff Kishner reduction. Ultimately you will get what, this C double bond O is converted to CH2. That means ketone is going to convert it to ketone get converted to CH2. Next again you do with nickel hydrogenation, so you are getting the steroid hormone. Okay, whatever. Then acetophenone is converted into ethyl benzene. So you see this is acetophenone, that is one ketone. Okay, C double bond O is there, CO, then C double bond O. Wolff Kishner reagent you use, it will, this CO group will convert it to CH2. Okay, ketone will convert it to methylene group. CH2 is methylene group. So you are getting ethyl benzene as a product. Then next acetaldehyde is converted into ethane. So you see here it is aldehyde. Okay, aldehyde, CHO. So in the previous slide I have mentioned that aldehydic group will be directly converted to alkyl group. Okay, so here you see CH3, then again CH3, so another alkyl will be added. That means C double bond OH will be converted to CH3 in presence of NH2, that is hydrazine, and KOH as a base in presence of glycol. So we are getting the byproduct as a nitrogen. I already mentioned that in the reaction we will get one N2 as a gaseous form. Gaseous nitrogen will be liberated out. So that's all about this two important reaction. So I hope you have understood. Thank you.